we have 1.60211 divided by 4.2. Okay, I get 0.381. Okay, because we are going for 3 decimal places, right? According to the output, yeah? We're going to go for 3 decimal places according to the output because they say ask you to show, right? This is the case. So meaning that I will write to 3 decimal places. The reason why is because of this. Yeah, if I use my calculator now, I'm not sure whether you guys are using the same. You get something like this, betul? You get something like this? All right. Now, then there's a tendency that what you're going to do is you're going to round off this one, you add one here. Then when you round off this one, you add one here, then here becomes 2. Tak boleh, yeah? You cannot do that. If you want the actual figure, you straight away take to this part only. You can only do this. If you want to 3 decimal places, take the 4th digit and check whether you can round off or not. All right. So that's why this is okay. Now let's look at what happens to the right hand side. Right hand side, we are going to multiply this, yeah. 1.60211 times 3.51. We get 5.623. Now, regardless of which formula you use, this one will never be anywhere close to this. So that's the reason why I asked you to only verify the lower limit. Now, do you know why this happens? Because of a lot of factors here, actually. Now, anything calculated using computer, right, is different from the way you do it manually sometimes. Because of number one, truncation. Truncation means you're rounding off. Here, if you use it from the output, they give you all the values, six or I mean it could be 12 digits or 18 digits or whatnot, right? And you reduce to this number. Over here, similarly, same thing happens. But then when it comes to the output here, they only display the values that they display here. That's why this is called displayed output, right? Displayed values. The value display here is usually very much truncated. So that's why you normally don't get what you expect to get certain times. And the worst is on the right hand side because now this one, instead of using the actual formula of 1 over f, you are using the other side of it. So another round of truncation going on, rounding off going on. So the right side is always very difficult to get, right? Only the left side is easier to verify. Okay, so that's the reason why I asked you to verify the left hand side and not the right hand side. Okay, clear? So a lot of mathematics involved at the back of it in terms of the rounding off, the truncation, right? The formula you use, you have the restrictions of your tables. You have to use this formula instead of the other formula. And then sometimes you may not even get the actual situation that actual nu1, nu2, you have to use a rounding off again, right? But bear in mind, whatever it is, the values won't run too far. See, this is 626, this is 623. So in terms of decimal places, the values won't run too far, right? Of course, if you get 5.4, then of course there's something wrong somewhere, right? But if you get 5.62 something, right, then it should be okay in that sense. So this one, this is what I would say. You must be able to reach a certain level of maturity for you to actually judge the solution that you get, whether it's logical or not. Number one, why is this happening, right? Why do you see situations so different from what you're supposed to have? What actually happened? Where do you go wrong? These are the things that sometimes you must stimulate your mind to think harder. With the AI generation, susah sikit, yeah, right? So think harder. It will help you a lot. Now, over here, we don't do what do you call that? Interpretation. For ratio or variances, we don't do interpretation. Because when you come to think about it, what can you interpret about a ratio? It's not giving you any values that is meaningful to the context of the problem, right? But we are interested in conclusion. When it comes to ratio of two variances, we are interested in conclusion. Interpretation is just telling you what these values are. And you cannot put in units for ratio, because when you work with ratio, you actually cancel out the units. It's just ending up with numbers alone. So no units. What are you actually trying to tell us? The value of your ratio here is more important for your conclusion. So what can you conclude here? So based on what I mean by conclusion here, we are going into what we call this question that I always like to ask. Okay, I've already given you the idea just now. So now you are going to tell me the answer. The question is this. Is sigma 1 squared equals to sigma 2 squared? Now, this is my question now. Based on the interval, yeah? Based on the interval. So you give me a thumbs up for yes, a thumbs down for no. Think first before you show me your thumb. Right. A thumbs up for yes, a thumbs down for no. A thumb down for no. If okay. Right, Ridwan is wondering now. Right? How come you change the decision? Follow the majority? Okay, right. Now, how do you know whether they are equal or not? The answer is yes, yeah. So nobody gave me a thumb down. Okay, it's yes because the value of 1 is in the interval. So, like I mentioned just now, yeah, how do you know whether, right, uh, they're going to be equal or not? Is when if sigma 1 squared equals to sigma 2 squared, you're going to get sigma 1 squared over sigma 2 squared equals to 1, where this ratio is actually here, right? You have the same ratio over there. And then if the value of 1 is in the interval, meaning that you can say that they are equal. Now, then can I ask you another question? Would the conclusion be the same? Would the conclusion be the same if you were to calculate sigma 1 over sigma 2 instead of a square? Instead of doing a sigma 1 squared over sigma 2 squared, you do a sigma 1 over sigma 2. Would the conclusion be the same? Yes, thumbs up. No, thumbs down. It should be a it should be a thumbs up, yeah? The conclusion will still be the same. Now, this is what happens when you look at this graph. Okay, let me show you this. Let me insert a page. I want to draw something. All right, now let's just check on this, yeah? This is your, hey, sorry. Why is my hand not so good? Okay, never mind. Okay, this is your y equals to x square graph, right? Then we have one more. I'm going to draw a black line there. Okay, we're going to have y equals to x graph now for black color. Okay, so this is 0 and 1, right? Because intersection between these two lines, right? X equals to 1, y equals to 1, x equals, if x squared is still going to be 1. So for this curve, the blue curve is still 1, 1. This one is still the same. So what do you notice? What you notice is that, right? If, right, if x squared is between 0 and 1, you also get or equals to 1. Your x will also be between 0 and 1. If your x squared is more than 1, your x value will also be more than 1. So it simply tells you that whether you're working out in terms of ratio your ratio sigma 1 squared over sigma 2 squared here, you have it as 0.381 just now and 5.623 can. When you take your standard deviation, sigma 2, you're actually taking a square root of this and square root of this. Now, both of this value will still be containing your 1 in the middle. It's just that the value that you get for the left-hand side, this value will be larger than this. This value, the one that you get on the right-hand side, this value will be smaller than this. You can calculate now. You press your calculator, you realize that left side square root of 0.381, okay, is actually larger than 0.381 up there. It's 0.61773, all right? Whereas square root of 5.623 is actually 2.371. So it's quite strange, isn't it? The range will be smaller, but you will still get 1 inside. This is exactly what happens to the curve. Because anywhere between 0 and 1, your x value is greater than your x square. That's why your x square value is smaller. When you take your square root, you get a larger value. But anywhere after 1, when you square up the value, it will go much faster, much bigger. So that's why square root of 5.6 here will give you about 2.37. This is much smaller compared to the 5.6. But over here is the other way around. So this is what happens when you look at the graph, yeah? Because this graph is below your black color graph. So that's why the value is smaller for square. But here the square is larger than your x. So this is the interesting part, yeah, about your graph, right? About your graph and about the values. So like it or not, you always would get the 1 in any of the range, right? That you're going to work with. So it doesn't matter whether you're going to check on standard deviation or you're going to check on variances. They are still going to give you the same conclusion. If 1 is in the interval for ratio of variances, 1 will also be in the interval of ratio of standard deviations. Okay, right? So this is the theory, yeah? Great. So itulah dia. Now you're done with all the basic that you need to know about this topic. We're going to start the real thing, as in how you're going to go about doing this. Let's look at example 24. It says here, a study was conducted by Department of Zoology at Virginia Tech to estimate the difference in amounts of the chemical orthophosphorus measured at 2 different stations on the James River. Right, so this is the scenario. Now, your orthophosphorus was measured in milligrams per liter. Yeah? So this is your unit. Now, there are 2 samples here actually. The first sample says that 13 samples were collected from station 1. Yeah? You get 13 samples from station 1 and you get 11 samples from station 2. 11 samples coming from your station 2. And there's a missing word here actually. There's a station 1 here missing. So the 13 samples from station 1 had an average orthophosphorus current content of 3.84 milligrams per liter and a standard deviation of 3.07 milligrams per liter. Right, for what we have here, let's write down all the information we could. Yeah. So start with, let's look at sample 1. All right. Sample 1, we have N1 equals to 13. And sample 2, we have N2 equals to 11. Right. Now, second sentence, the subsequent sentence is this one. Look at this part of the sentence. It actually tells you that the 2 values of 3.84 and 3.07, they actually were obtained from your 13 samples here. In other words, you get x bar 1 to be 3.84 and S1 to be 3.07. Can you follow? Because that is about your standard deviation of your sample. So that's why it's S, yeah? Right? It's S and not sigma or not even S squared. Right? It's only S. And if you read further, from station 2, X bar 2 is 1.49 and S2 is 0.80. Similarly, both of the two values here, 1.49 and 0.80, they were obtained from your 11 samples of station 2. And then here it says, assume that the observations came from normal populations, right? So basically what you know is that based on these two, if you want to check on means, you have this problem of sigma unknown, all right? Now, if you have sigma unknown, you will have to know what would the assumption of your variances be. But if you notice, this question doesn't tell you the assumption of variances up to this part, right, that we have discussed. Therefore, part A is important. Look at what part A says. Construct a 98% confidence interval for the ratio of two variances and standard deviations, right? Based on the confidence interval, what can you conclude about the two population variances? Now, because this is an example, I give you two of this. One is for two variances, the other one is for two standard deviations, because this is an example. In your assessment, we normally will ask you to do either one, right? Whether it's going to be variances or just standard deviations alone, right? We won't ask you to do both. But for this one, we'll do both because we're going to cover this so that I don't have to come out with two different sets of questions. Okay, so now it says here you're given 98% confidence interval, yeah? And then what you want to do is you want to find ratio of two variances. So I suggest this, yeah? Write this down if you see it. See, once you write down the symbol, then you know what you're looking for. And this one will tell you alpha equals to 0.02. Okay, so A. We have, we want to look for ratio of two variances. If you check back the list of appendix that you have here, ratio of two variances, we need your F. So always refer to your appendix, yeah? Make your appendix your good friend, right? And then we have alpha equals to 0.02 simply means that we need two values now. One is 0.01. Now, what is your new one here? What is your new one here?
12.
12. Now, what do you decide on 12? First of all, you actually need to check on this, yeah, these two. You realize that S1 squared is actually greater than S2 squared. So this is okay. Then only you take nu1 to be 12 and nu2 to be 10, right? N minus 1, yeah? Now, if you check out S1 squared is not greater than S2 squared, then what you do is you just switch, right? Make sample 2 your sample 1, sample 1 your sample 2. Just interchange. It's very simple only, just interchange. That's why at the end of the day, everything comes back to the ratio that we work with because it's a ratio, so it doesn't matter which one comes first. But the condition we have to follow. So we follow the condition of S1 squared must be greater than S2 squared. Okay? So nu2 here is 10, yeah? And then we have one more, 0.01. Then now our nu1 here is 10, nu2 here is 12. Now, if you want to put nu2, nu1 also, it's up to you. It's entirely up to you. I don't have any objections about how you want to represent these two. But the point is the numbers here, the figure here must be correct because that is what you're going to refer to inside your table. Okay? So let's look at a table. Can you give me the number, please? F 0.01, 12, 10. What is the value from the table? 0.01, yeah?
4.7.
4.7. 4.71. Okay, right. 12 here, all the way down to 10. Here, your 10 is here. And then we want 0.01. 0.01, according to the order, is the third one, right? So that's why you're right. It's 4.71. It's the third value, yeah? Okay. So we have 4.71. All right, one more. 10, 12.
4.30.
4.30. Very good. See, it's so easy. The minute you get these two numbers in your exam, you straight away get two marks. 2 marks, So easy to get, right? So make sure you know how to read the table, you know how to work with the critical value. These are the critical values, yeah? Right. So once you get this, we can work with our confidence interval. We want 98% CI for sigma 1 squared over sigma 2 squared. So once again, put in the values. Right, so we want S1 squared over S2 squared. The formula is this. So 3.07 squared over 0.80 squared multiplied by 1 over 4.71. You follow your formula, yeah? And then multiply by 4.30. And let's see what we have here. Okay, do you get what I get? Okay, right. Very good. So now our 98%, because the question wants two, yeah? Both, yeah? Sigma 1 over sigma 2, standard deviation now. Sigma 1 over sigma 2. So it will just be the square root of 3.1266 and square root of 63.3235. This is 1.7682 and 63.3235 will give us 7.9576. Okay, so that is it. That it is. That would be the first part of the question, yeah? Construct a 98% confidence interval for the ratio of two variances as standard deviations. So the second part is, based on the confidence interval, what can you conclude about the two population variances? So the word here is conclude. Okay. They want you to come up with a conclusion based on your calculation here. What can you conclude about the two population variances? So we want a conclusion. So how do you conclude here? Are they going to be equal or not equal? That is how you're going to conclude. Equal or not equal?
Not equal.
They're not going to be equal, yeah? So you can mention this. Since the value of 1 is not, yeah, is not in the interval, sigma 1 squared is not equals to sigma 2 squared. Assume. All right, that's it. So now, if you don't want to use variances, you can talk about sigma 1 not equals to sigma 2. It's still going to be the same, yeah? Because like I mentioned just now, if you notice, 1 is still not going to be inside this interval, even though the value is smaller, right? Closer to 1, but it's still not inside. Because both of these values are I mean, both of these values are more than 1. That's why the value here is lower than the one up here. Just now was different, can? So this is how you get your conclusion. So after your conclusion that you work out here, you read the second part of the question, part B. B says that from the result in A, construct a 98% confidence interval for the difference in the population means amount of chemical autophosphorus measured at the two different stations. Okay, let's read carefully. The difference in the population mean amounts of autophosphorus measured as these two stations. Now, we are now interested in mean tau, mu, population mean, yeah, this one, mu1. And then they want to see the difference. This part, the word here is difference. So the difference here will tell you mu1 minus mu2. Okay, so this is what we want. So you have to read the question. Just now, the first part was ratio of two variances. Now is the difference of the population means here. All right. So if you want to work with mu1 minus mu2, you go back to your appendix here. All right. Look for mu1 minus mu2. See, for your appendix here, it shows that mu1 minus mu2, you need the assumption of your variances. Which one is the one that you're going to assume here? So you need to assume the second one, sigma 1 squared not equals to sigma 2 squared, based on the interval that you constructed up here. See, from the result in A, that means what you have found out from A, you concluded that 1 is not in the interval. This is unequal variances assumed. So when you have unequal variances assumed, meaning that when you work out your second part, you will need to assume unequal variances. You need to check out this formula instead of the first formula up there. Can follow? All right. So if that is the case, now there are a few things that you need to do first. Yeah. Okay. Before I go further, yeah, I want to remind you of one thing, or just want to inform you first because it's the first time you see this, right? I want to let you know this, yeah. For any situation dealing with your confidence interval, where both of them are related in the same question. For example, the first part is your variances, second part would be the mean, right? You're interested in the means here. Please make sure that the two confidence level, they are exactly the same. If one is 98 and the other one is 95, then they are not workable because you cannot base your conclusion of different confidence level, right? Your conclusion must be based on the same confidence level. Even if you have to work out in the next chapter, we may still use this. We will be looking at alpha. If your confidence level is 98%, you need to make sure that your alpha is 2%. Otherwise, they are not workable, right? We'll come to that one next chapter, yeah? So next topic, you get ready your notes tomorrow for that one because we're finishing this topic today. Okay, so make sure, yeah, the two of them are exactly the same before we work on it. So now both of them are 98%. It's just nice. We can continue with the working. So let's continue with this. So from A, right? This is your B, yeah. Did we label? Okay, we did. Make sure you label your answers, yeah. From A, sigma 1 squared not equals to sigma 2 squared, assume. Meaning that now, first thing first, we need to look for your degrees of freedom, right? Your nu here. Your nu here will be S1 squared over S2 squared. So we're going to take this one, yeah? This part, right? 3.07 over 0.80 squared plus, sorry, not 0.80 squared. S1 squared over N1 squared, yeah? N1 squared is 13, not squared, 13. S1 squared over N1. And S2 squared over N2, which is 11 square over S1 square over N1 squared divided by 12 plus S2 square over 11 square over 10. You use the formula inside your appendix, yeah? If you cannot, if it's hard for you to see it from the screen. And then after that, you check out the calculation. Do you get this? Do you get this? Or did I do a wrong calculation? Too many squares, yeah? Just be careful. If you get a different answer, let me know, yeah? I'm not very good at calculator skill, actually. At least there's a thumbs up. I hope both of us are not on the same boat. Let me just double check. And then, okay. What about the rest? Okay. All right, very good. At least I have a few more thumbs up. Thank you, girls and boys. Right. So now, what are we going to take here? We're going to take the value of 13, yeah? Make sure you take the value of 13. You have to round down. Okay. This one is rounded down. You need to take the value of 13. It doesn't matter how large this decimal is. The important part is the integer in front here. Can follow, yeah? So now we have that. We're going to look for critical value. Your critical value here is going to be t, yeah? Because we are going back to t distribution now. So we have 0.0113. Let's check this out from the table. T table, yeah? Page 17. 0.01. 2.650, correct? Okay, very good. So now we have got we've got a degrees of freedom, we have got your critical value, we are ready for our confidence interval. 98% CI for mu1 minus mu2 here. We're going to take x bar 1 minus x bar 2, right? Because we start with mu1 minus mu2. So x bar 1 minus x bar 2 will be 3.84, this part, 3.84 minus 1.49. 3.84 minus 1.4. Okay, right. Minus of and plus minus 2.650. Okay, since the degrees of freedom, since the variances are assumed unequal, we only have one formula here, which is 3.07 squared over 13 plus 0.80 squared over 11. Okay, let's look at this interval now. Have you found your answer? I got a wrong calculation. Times square root of something is wrong. Do you get the value that we're supposed to get, or the value looks funny? Oh no, the value memang very small. Sorry. I got it already. Wait, 1 minute. Okay, times 2.65. Okay, then okay, one of it is 0. Wait, value is super small. 0. Why is it not writing? Just give me a minute. Oh no, it's not allowing me to write. Just give me a minute. Let me save this. Zero, 0.0048. Can. And then 4.6952. Okay, very good. Right. So we have this. Now, if you want to interpret, the context is the one that I underlined here, right? When 98% confidence that the difference in the in the population mean amounts of chemical for the two station is between the two values here. And don't forget your units is measured in milligram per liter. But according to this question, they don't want you to interpret. They only want you to conclude. Based on the interval, is there a significant difference in the two population means? Okay, so how are you going to answer this? Based on the interval, is there a significant difference in the two population means? Yes or no? Based on this interval. Yes, thumbs up, no, thumbs down. The question is, the question is mu1 equals to mu2 or not? That's the question, right? Is mu1 equals to mu2? No, sorry, no, sorry. Is mu1 not equals to mu2? This is the question. There's a significant difference. So the answer is yes, yeah? Because 0 is not in the interval. Now, even though this question doesn't ask you for the justification, but I always write down the justification because your assessment, we will ask you for justification. right? So you write down there, yes, because why? Zero is not. Yes, here simply means that there is a significance difference. Yeah, there is a difference, right? Difference. So meaning that mu1 is not equals to mu2. Why? Because zero is not in the interval. So now this question itself tells you two things. Yeah? One is about zero, the other one is about one. Zero is for mean, one is for variances. Is that clear? Right. So today's lesson is very straightforward. Yeah. Basically is what you need to find out regarding your ratio of two variances. Right. And why do you need that is because you need the assumption to work on the difference in two population means. So that is always what you need to start with, right? So look at this part here, the last part. This will conclude up today's lesson. When considering the confidence interval for the ratio of two variances, this is the last page of your notes here. If the value of 1 is in the interval, then you can conclude that the two variances are equal. But if 1 is not in the interval, then we can conclude that they are unequal, right? Variances assumed. So to draw conclusion on the confidence interval for difference of two population means check if the value of 0 is in the interval. But if you want to check on two population variances based on the ratio, then you need to check on the value of 1, whether it's in the interval, right? And then, of course, from then you work with the other procedures required to check on the confidence interval. Okay, so that's it about your confidence interval, right? Sorry, I've taken up some of your time, but this will be the last part of your chapter 2 or topic 2. Um, simply means that we have just completed the estimation part. That means we're just dealing with confidence interval, nothing but confidence interval. Next topic that we're going to cover tomorrow, we're going to look at the outside, right? When you look at confidence interval, it's the inner part, yeah? It's the inside of your distribution. Wait, where is it? Where is it? Where is it? I didn't draw anything today, so we can use the one earlier. Right. Okay. So when we talk about confidence interval, we're interested in the one inside here. Tomorrow, we're going to start talking about the ones outside here, right? So we're still going to look at the same idea. So the point is this. If you can understand what we discussed in this topic here, the rules will still be applied to the one that we're going to discuss tomorrow. But it's just that how are we going to extend from there? And then at the end of the day, when we look at the work questions or the situations given to you, we're going to combine both topics 2 and topic 3, right? Both topics will be combined to check on your understanding because one is inside, one is outside. They are actually related. So this is the part where I actually left out all the tests inside your um, outputs, right? So tomorrow we'll look at something different. But please make sure you check out what you don't understand from confidence interval first. We sort that one out before we start with tomorrow's topic, that is hypothesis testing. Okay, so remember to download your notes for topic 3. We're going to start that tomorrow in class, yeah, physically. All right. Okay, so now you are all ready for your topic 2 tutorial questions. You can start working on them. Start from the mixed questions, right, to see your understanding on that. Now, prepare yourself early because that part will be in your test, which is on week 13, right? It will start from this topic onwards, yeah? Topic 2 onwards on estimation until topic 4. And then your assignment also requires topic 2 and topic 3. We're going to mix those questions. Okay, so tomorrow will be one more lesson before your test week and also your mid-semester break. So I'll see you a long time after that. So you better come to class tomorrow, otherwise you will miss me instead of me missing you. Okay, right. So thank you very much. Take care, everyone. All right. So I'll see you tomorrow, yeah, in class. So thank you and take care. Bye bye.
Thank you, Miss.
Right, thank you.
Thank
Thank you.
you.
Thank you. If you still have questions, you can ask. Okay.